Okay, junior lab rats. I don't know what happened, but we didn't get the video up during class, and then I made a second video just for you after class, and that one didn't show up either. So now we're going for the third time as a charm, especially since two of you were absent today. So just real quick, I want to go over your notes. Don't mind Drew in the background. Wave, Drew. You can be seen over my shoulder. Yo. Okay. Oh my gosh. Did you seriously? Okay, so here we go. All right, so today's lesson was lesson 13, and the lab was raising a sunken ship, and hopefully some of that information will show up in the forums. Check with your lab team captain because most of them turn stuff in today. But we'll be sure you can get the information, especially Traveler and Sky who were missing. All right, so we were doing forces and fluids today. We will start right here at the first page of notes, and you can make sure that you've filled in the blanks correctly. So with buoyancy, buoyancy is the ability of a fluid to exert an upward force on an object placed in it. Buoyancy results in an object appearing to be weightless in fluid. Appearing still has weight. Buoyant force acts in an upward direction, acting against the force of gravity, so it makes an object feel lighter. Right? Doesn't mean it is lighter. So we talk about the sky today. Archimedes, this fellow right here. Hello. And anyway, he was Greek. He was a mathematician, physicist, engineer, inventor, and astronomer. And if you are well practiced in a lot of disciplines, if you guys remember that word from like our probably third or fourth lesson, it's polymath. He's a polymath. Good for him. And he gave us this principle here, which says Archimedes' principle relates to the amount of fluid an object displaces to the buoyant force of the object. Archimedes' principle states that the buoyant force of an object is equal to the weight of the fluid displaced by the object. All right, so there's this awesome story about him. All the information's here, so I'll let you read it. But to summarize, because it really is fun, and it is a legend, it's the stuff of legends. It's probably not exactly how it went down. But the legend is that a king commissioned a golden crown, and he wanted to make sure that the goldsmith had been honest with him and that the crown was made of solid gold and not some other metal melted in with it. And the goldsmith didn't keep gold for himself. So basically, he wanted to know if the crown was solid gold. And so he gave Archimedes this job, and Archimedes had to figure out a way to determine whether the crown was made of gold without damaging it. So the story is that he needed to figure out the volume of the crown. And one day he sat in the bathtub and the water level raised. And when that happened, he realized that that was the whole concept of displacement. The body goes in, the water goes up. Oh, I can do this with a crown. And that way I can find the volume of the crown. And then he was so excited that he jumped out of the bathtub, stark naked, dripping wet, and ran down the street screaming, Eureka, 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 which means I have found it. And yeah, stark naked and dripping wet, just running down the streets. Can you envision this old Greek guy running? I don't know how old he was then. Running down the street. So anyway, that's the idea. And in the end of the story, the idea is that he proved that there had been silver mixed in. And we don't find out what happens to the goldsmith, but it probably wasn't good for him. So we get to this concept here, floating and sinking. All right, first things first. This triangle, I sent out an email this afternoon. This triangle had a mistake in it, and the mistake is right here. You see where my cursor is pointing? Right there. So hang on, I'm going to come back and explain that in just a second, but I'm going to open this because I'm going to show you the corrected version. Okay, here's the corrected version. Well, if it'll open, look at that. I love the spinning Windows wheel. Oh, that's super when I want it to do something. We'll come back to it. Go here first. So an object that is more dense than the fluid it is immersed in will sink. An object that is less dense than the fluid in which it is immersed will float. And an object with similar density to the fluid it's in is going to be suspended. So here we have our floating object. It's less dense than the medium. We'll call this liquid the medium. We don't know if it's water. It could be alcohol. It could be oil. And this particular green block is going to have about the same density. So it's suspended. Whoa. Okay. We'll come back to that. Give me a hard time there. Whoops. Man, there we go. And then this yellow one is going to be more dense, or denser, which is actually a word. It doesn't sound like it is. Denser than the fluid, so it's going to sink. So we're going to come back to this triangle in a second if it'll let me open. I don't know that it will. So we have buoyancy and density. So looking at these two little ships, it says a block of steel sinks in water. A steel ship with the same mass floats on the surface. So why does a boat float? It's not less dense than the water. It does not weigh less than the water. The shape of the hull, which is this part of the bottom of the boat right here, displaces, oh my goodness. Wow. I just keep getting an error message like popping up. The shape of the hull displaces a volume of water equal to the part of the boat submerged. So if you can imagine that you see the surface of the water here, if this hull were not filled with air, and if it were filled with water, it would take up a certain amount of volume, about the size of this purple section. But because it's filled with air, it displaces that water. So it moves the water elsewhere. And in an ocean, you're not going to notice it. But if you were in a bathtub like Archimedes, maybe you would. We're going to go back to that triangle in a minute so I can make it open up. Bernoulli's principle. Okay, Bernoulli's principle states that the faster a fluid moves, the less pressure the fluid exerts. This is fancy math, which shows the exact same thing. Okay. Bernoulli's principle states that the pressure exerted by a moving stream of fluid is less than the pressure of the surrounding fluid. And it is Bernoulli's principle that makes lift possible. So we did a quick little example in class today. We had a big long bag. It was probably 10 feet long, maybe 6 inches around. Hey, I'm recording a lesson real quick because I messed it up. You were upstairs. So anyway, big long bag. And I had Jack hold it and try and blow into it. And he didn't get a whole lot of air in because it was a big, big long bag. But I held it out from my face a couple of inches and blew real gently, and it filled right up. And we'll try and do, since 2 of you missed it, we'll try and do that again next week, maybe just for fun. So if you look right here, it's got a diagram of lift, okay? And this is basically how Bernoulli's principle, that's a fun word, makes flight possible is through lift. And you can think of lift and buoyancy similarly in that there is high pressure below causing an upward force, which is working against gravity. So here with the wing, you've got air coming straight at the front of it, and then it is divided when it hits the wing, and the air beneath is going to pass over a shorter distance because this is a straighter edge, whereas this is a big curve and it's a longer distance. So the air that passes beneath will pass with low velocity because it's trying to get here at the same time, but it's going to have higher pressure because of Bernoulli's principle. Now up here, your air is going to pass with higher velocity because it's trying to get over this same distance. It's a longer distance on top, shorter distance on the bottom, same amount of time. So it's got higher velocity but lower pressure, and this higher pressure underneath causes lift and the wing goes up. Lastly on here, we have this section that showed how Bernoulli's principle can be used with things like spray bottles and atomizers. This is an atomizer. Sometimes you see them in old movies. There's always a fancy lady puffing on it and spraying perfume. But if you look right here, it explains how it works. You've got this little straw that comes down into the liquid. You have a little bulb over here. And when this is compressed, the air is pushed this direction through the tube as it moves with higher velocity across the top here. All right, that's going to be lower pressure. And when that lower pressure is created at the top of this straw, it actually causes a little bit of a vacuum, which sucks this liquid up. And then when it hits the air, it gets kind of sucked into the airstream and blown out like a mist. And that's how an atomizer works. Spray bottles used on lawns use this same principle, except instead of air here, it's typically the hose. And so you have water, that's the fluid this time, instead of air being the fluid, and it flows across quickly, which then of course is going to do the same thing. It's going to reduce your pressure on top, and it's got to have high velocity, low pressure, and it's going to cause the liquid in the spray bottle to come out, mix with the water, and spray out on the lawn. So if it could be an herbicide or a pesticide, and that mixing with the water is intentional too, because usually what's in the bottle is more concentrated. So it says spray bottles like those used to spray lawns take advantage of Bernoulli's principle in their design. Atomizers function similarly, using pumped air as the fast-moving fluid to reduce the pressure at the top of the straw and draw the liquid up. Real quick, here were your homework questions and answers. What does Bernoulli say about the pressure exerted by a moving liquid? So everybody's answer may be a little different, but we need to go back to Bernoulli's principle right here, that the faster a fluid moves, the less pressure it exerts. That's the general idea. And then in order for an object to float, it must either be less dense than the fluid is in, or it must what? And this answer is going to be displace the same amount of water in which it is submerged, or same amount of fluid. In this case, we're talking about boats probably. So go right there to that image if you need to review. And lastly, draw a wing. Ta-da, there's a wing. You can draw a wing diagram. With this one here, be sure that you are using the language about displacing the same amount of water in which it is submerged when you're on your test. If you use other language, like involve the word weight or whatever, it's not going to be the correct answer. So let me try one more time to open this one. If it doesn't open, I will just kind of try to explain to you what I mean, but I don't know, maybe it's here. Oh, here, let's do it this way. All right, so here's what we're dealing with. This is what I wanted you guys to have a quick look at. So there was a mistake on that graphic. See right here where it's divided by? It's not divided by, it's times. So here's how this graphic works. Look right here down this line. See where the cursor's going? Okay, you have a D and an M. So you have a density and mass here. Which of the three letters of the triangle is missing? This guy right here, okay? So when you look over here, that means this side is going to give you the one that's missing, that's volume. If you memorize this center triangle right here, you will have all three formulas memorized. Oh my gosh, what was that? That was fun. Oh my God, Becky, look at her butt. Okay, volume equals mass divided by density. Look here, here's mass. It's on top. And there's your division symbol. Remember that your mass is on top, and then you get mass divided by density, because density divided by mass is not the same thing, right? Okay, over here, you have an M and a V. What's missing? The D. There it is, density. Density equals mass divided by volume. Again, mass is on top, volume is on bottom. Now remember this one on the bottom, right there, there's a tiny little mistake that I saw in this diagram. So we want to ignore this. We talked about this in class today, and we used all the right terminology and all the right formulas. And then when I went and looked back at it, I was like, oh my gosh, when they wrote it the second time, good night, love you. See?
I'm your density.
Yep, you're my density. So here you got density and volume. What's missing? Mass. So this is the formula for mass. Mass equals density times volume. Ignore that, ignore that, ignore that. It's wrong, it's wrong, it's wrong. So if you memorize this middle triangle, you're good to go. And somebody pointed out today that it actually says DMV if you're moving left to right. So maybe that'll help you remember, you know, like the place you get a driver's license, divided times. All right, and that is really all you guys need to do. So if you can memorize that triangle, it would be good for your test, and I'm gonna let you go because that's the end. But yeah.